Right now, off the coast of Oregon, two tectonic plates are locked together. One is trying to dive beneath the other refuses to move. That standoff has been building for over 300 years. When it finally breaks, scientists say it will shake the Pacific Northwest for up to 5 minutes straight, drop sections of coastline into the sea, and send a wall of water towards shore. We will look at the fault nobody talks about enough. The tsunami clock already ticking, and the scenario where two disasters hit the west coast at the same time. If you enjoy this journey, a like and subscribe means everything. Now, let's go. Stand on the Oregon coast and look west. The Pacific looks calm, waves roll in, seagulls drift, and everything feels solid under your feet. But about 50 miles offshore, something enormous is happening in slow motion. Two of the largest pieces of Earth's outer shell are pressing against each other with a force that would crush a skyscraper like a soda can. One plate wants to slide beneath the other refuses to give way. That battle has been going on for over 300 years without a single release, and the ground beneath your feet is paying the price. The Pacific Northwest sits on top of one of the most loaded geological systems on the planet. The Cascadia subduction zone runs for over 600 miles along the coast, stretching from northern California all the way up through Oregon and Washington into Canada. That is longer than the distance from New York City to Chicago. And along every mile of that boundary, stress is building. Here is what makes that stress dangerous. When two plates lock together instead of sliding, the rock does not stay still. It bends. The edge of the North American plate, the ground that Washington and Oregon sit on, slowly warps downward toward the sea. Meanwhile, the inland part of the continent keeps pushing forward. Scientists have measured this. The land east of the Cascade Mountains is inching toward the coast by fractions of an inch every year. The whole region is being compressed like a slow-motion car crash that has lasted 3 centuries. Think of it like pressing your palms together and trying to push one hand under the other. If your hands stay locked, your arms bend, your shoulders strain, everything loads up. And the longer you hold it, the more violent the release becomes. Geologists call this elastic rebound. The rock stores energy the same way a stretched rubber band stores energy. When the lock finally breaks, all of that stored motion releases at once. In Cascadia's case, 300 years of bending snaps back in a matter of minutes. The coast lurches westward, the seafloor lifts or drops, and the shaking begins. What scientists have measured over the past few decades is sobering. Instruments along the Oregon and Washington coast show the ground is tilting. Tide gauges show the land slowly rising in some spots and sinking in others. The entire region is deforming under pressure that has nowhere to go. A team at the University of Washington compared decades of ground movement data and found patterns that match what other subduction zones looked like before their major ruptures. The fault itself sits mostly offshore, hidden beneath miles of ocean water and seafloor sediment. You cannot see it, you cannot feel it moving, but the evidence of what it is doing shows up in every tide gauge reading, every GPS sensor, and every millimetre of ground tilt recorded along the Pacific Northwest coast. And what makes Cascadia different from almost every other dangerous fault in America is exactly that invisibility. The San Andreas in California breaks regularly. It rattles cities and reminds people it is alive. Cascadia does none of that. It sits quietly offshore, locked and loading, giving no obvious warning. No small quakes bleeding off pressure. No visible cracks in the surface. Just silence and stored energy. That silence is the most unsettling part of all. Because somewhere beneath the Pacific Ocean, the two plates are still pressing, still locked, still bending the ground above them, and the longer that standoff holds, the bigger the eventual release. What exactly is down there? To understand that, you need to understand what a subduction zone is, and why the one off the west coast is built in a way that separates it from every fault most Americans have ever heard of. Most people think of earthquakes the way California shows them, a crack in the ground. Two plates sliding sideways past each other, a sharp jolt, and then it is over. That is the San Andreas model. It is violent, yes, but it is a scratch compared to what a subduction zone can do. The subduction zone is a completely different machine. Picture two enormous slabs of rock, each one dozens of miles thick and hundreds of miles wide. One of them is made of dense oceanic crust, the heavy dark rock that forms the floor of the ocean. The other is lighter continental crust, the kind that holds up entire mountain ranges and cities. When these two slabs collide, the heavier oceanic one loses. It dives. It slides beneath the lighter continental plate and descends at an angle into the hot interior of the Earth. That diving process is called subduction, and it is the most powerful geological force on the planet. The biggest earthquakes in recorded history, the ones that rewrote coastlines and sent waves across entire oceans, all happened at subduction zones. Chile in 1960, Alaska in 1964, Japan in 2011, each one a megathrust, each one powered by the same basic mechanism happening right now off the coast of Oregon and Washington. The Cascadia subduction zone is where the Juan de Fuca plate, a piece of oceanic crust about the size of the state of California, meets the North American plate. The Juan de Fuca plate is losing that contest. It is diving beneath North America at a slow but relentless pace, and as it descends, it drags the edge of the continent down with it before eventually snapping free. What makes a megathrust earthquake so different from the San Andreas style is the scale of the fault surface involved. On the San Andreas, the two plates slide sideways. The contact zone is relatively narrow. In a subduction zone, the two plates press against each other along a massive sloping surface, sometimes hundreds of miles wide and hundreds of miles long. When that surface ruptures, the shaking does not come from one point. It comes from an area the size of several states all breaking at once. In Cascadia's case, that rupture surface stretches from Northern California to British Columbia. A rupture there does not produce a sharp jolt from a single spot. It produces a rolling, heaving wave of energy that radiates outward from a fault zone larger than most European countries. The depth matters too. Near the coast, the boundary between the Juan de Fuca and North American plates sits roughly 9 to 12 miles underground. Farther inland, beneath the Cascade Mountains, it descends to 50 or 60 miles deep. That geometry means a Cascadia rupture affects not just the coastline, but communities well inland, including major cities like Portland and Seattle. And then there is the ocean. The San Andreas runs through land. Cascadia runs mostly underwater. When that underwater fault snaps, it does not just shake the ground, it moves the seafloor. A section of ocean floor the size of multiple football stadiums suddenly lurches upward or drops, displacing an enormous column of water above it. That displaced water has to go somewhere. It goes towards shore. That is the part that separates Cascadia from almost every other earthquake threat in America. It comes with a built-in ocean weapon. And understanding the scale of that weapon starts with understanding the plate that is doing the diving, moving slowly, silently, and without rest. 1.5 inches per year sounds like nothing. It is slower than a fingernail grows. You would never feel it, never see it, never notice it in any single lifetime. But that tiny annual movement is one of the most consequential forces on the West Coast, because it never stops. The Juan de Fuca plate pushes toward North America at roughly 1.5 inches every year, year after year. Decade after decade, century after century. Over 300 years, that motion adds up to nearly 40 inches of total movement. That is more than 3 feet of plate pushing that has had nowhere to go, because the two plates are locked together at their boundary. The motion does not disappear, it gets stored. Think of it like winding a clock spring. Every turn adds a little more tension. The spring does not break on the first turn, or the 10th, or the 100th. But at some point, the stored energy becomes too much to contain. The spring releases all at once. geologists use GPS sensors anchored to the ground across Oregon and Washington to track this slow deformation in real time. The readings show the land compressing, the coast moving slightly eastward, the inland areas moving in a different direction. The whole region behaving like a surface slowly being bent by a force underneath it. What makes this accumulation especially alarming is that it has been going on since the last great Cascadia earthquake in January of 1700. That rupture released the stored energy of centuries. Then the plates locked again and the process restarted. For over 300 years now, the Juan de Fuca plate has been pressing, bending and loading the system back up. Scientists calculate the total energy stored by looking at how much movement has accumulated and where the plates are locked most tightly. A team studying Cascadia's locking patterns found that some sections of the fault are storing motion at nearly 100% efficiency, meaning essentially zero energy is bleeding off through small tremors or slow sliding. Everything is being saved up. Compare that to a fault like the San Andreas, where sections release small earthquakes regularly, bleeding off stress in manageable chunks. Cascadia in many areas does the opposite. It holds everything. Now multiply that stored motion across a fault zone 600 miles long. Each mile of that locked boundary has been compressing for 3 centuries. The total energy locked inside the system is staggering. Scientists estimate a full Cascadia rupture would release energy equivalent to thousands of the largest nuclear weapons ever tested, all going off simultaneously beneath the ocean floor. That is what 1.5 inches per year becomes when you give it 300 years to accumulate. But here is the part that keeps seismologists awake at night. Nobody knows exactly how much of the fault is locked at any given time. New measurements from offshore instruments suggest some sections may be more loosely coupled than others, meaning those parts might slip more gradually. Other sections appear to be clamped tight. The problem is that a loosely coupled section does not mean a safe section. It may simply mean the energy releases in a different way, or that the rupture from a locked section next door triggers it anyway. The fault is not a simple uniform surface. It is complex, uneven, and still being mapped. And the deeper scientists look, the more they realise how much remains unknown about exactly where the pressure is highest. That question of where things are locked tightest, and where they might break first, leads directly into the most chilling concept in all of Cascadia's story. If you lived near a volcano that had been erupting every few years, you would take it seriously. The noise would remind you. The smoke would remind you. The small lava flows would remind you. Now imagine a volcano that had shown no activity for over 300 years. No smoke. No rumbles. Just a perfectly calm mountain. Would you be more worried or less? Most people would feel safer. That is the same mistake millions of people are making about Cascadia right now. The Cascadia subduction zone is one of the quietest major fault systems on Earth, and that quiet is the danger. Most subduction zones around the Pacific make their presence known constantly. Japan's subduction zones produce hundreds of small earthquakes every year. The fault systems along South America shake regularly. Chile alone has recorded dozens of significant quakes in recent decades. These constant small events bleed off energy, remind communities to stay prepared, and give scientists data to work with. Cascadia produces almost none of that small activity near its locked zone. The stretch of fault running offshore from Northern California to Washington is remarkably still. Weeks pass without a notable tremor in the region directly above the locked interface. Months pass. The ground above one of the most energetically loaded faults on the continent just sits there, quiet for a long time. Scientists actually used that quiet to argue Cascadia was not dangerous. If the plates were truly pressing together as hard as subduction theory suggested, why were there no earthquakes? Some researchers in the mid-20th century genuinely believed Cascadia might be a passive, unlocked boundary that would never produce a major rupture. That argument collapsed completely in the 1980s when geologists began finding drowned forests along the Oregon and Washington coastlines, stands of ancient trees still rooted in place but buried in saltwater mud. Those trees had died suddenly when the land dropped during a massive earthquake. Scientists also found layers of sand far inland from the modern coast, tsunami deposits left by enormous waves, and they found matching records in Japan. The evidence was undeniable. Cascadia had ruptured before, repeatedly at enormous scale. The quiet had meant nothing. The fault had simply been storing. Scientists now understand why Cascadia is so quiet. The plates there are locked so tightly, and the locking is so complete in some zones that stress does not bleed off in small increments. The system builds pressure the way a pressure cooker builds steam. Everything stays sealed until the seal breaks all at once. Small earthquakes require some movement. Where there is no movement, there are no small earthquakes. The absence of noise is evidence of how completely the fault is clamped shut. A research team studying locking patterns across Cascadia estimated that certain sections of the fault are storing energy at rates that rival the most dangerous subduction zones in the world, despite producing almost no detectable seismicity at the locked interface itself. That finding flipped the old assumption completely. The silence means the plates are grinding with such force that nothing slips at all, and the longer nothing slips, the larger the eventual rupture has to be to release the accumulated strain. Right now, every quiet day on the Oregon coast is another day of pressure stored. Every calm week is more energy locked into the system, but the silence does not last forever. The geological record makes that clear, and the last time that silence broke, the consequences were felt all the way across the Pacific Ocean. Imagine two massive sheets of sandpaper pressed face to face with millions of tons of force behind them. As long as the pressure holds them together, they do not move. They are locked. The rougher the surfaces, the more securely they grip. Now imagine those two sheets of sandpaper span an area bigger than the state of California. That is the locked zone beneath the Pacific Northwest. The locked zone is the section of the Cascadia Fault where the Juan de Fuca Plate and the North American Plate are frozen against each other. No slipping. No gradual release. Just two enormous rock surfaces clamped together under pressure so intense that the rock itself deforms rather than letting the plates slide. Geologists map this locked zone using a combination of GPS measurements on land, seafloor sensors, and computer models of how the ground is bending. The picture that emerges is not a simple flat line offshore. The locked zone is a sloping, curved surface that starts near the coastline and descends inland as the Juan de Fuca Plate dives deeper. Near the coast it sits about 9 to 12 miles underground. As it extends eastward and downward, it reaches beneath the Cascade Mountains at depths of 50 to 60 miles. The significance of that geometry is huge. It means the locked zone underlies a massive area. Seattle sits roughly above the deeper eastern edge of that zone. Portland sits above similar territory. The energy stored in the locked zone does not just affect the coastline, it affects the entire region above it. Scientists measure how locked each section of the fault is using a concept called coupling. A fully coupled section stores 100% of the motion. A partially coupled section releases some as slow creep. Measurements across Cascadia show high coupling in several critical areas, particularly in the offshore Washington and Oregon segments. Those tightly locked sections are the ones that carry the most stored energy and would drive the largest rupture. The locked zone also explains one of Cascadia's most dramatic physical effects. Because the leading edge of North America is being dragged downward by the subducting plate, the coast is actually subsiding very slowly over time. Then, when the fault ruptures and the lock breaks, that bent-down coast springs back upward rapidly. Some areas could rise by several feet in seconds. Other areas, specifically those farther inland where the plate was being pushed up under compression, would drop. The coastline would be physically reorganized by the earthquake itself. Studies of past Cascadia ruptures have found evidence of exactly this pattern. Sediment cores from coastal wetlands show layers where the land dropped suddenly during past earthquakes, drowning vegetation under salt water almost overnight. In some locations, that sudden drop was measured at 3 to 6 feet. Whole marshes became tidal flats in a single event. Now picture that same drop happening to modern coastal neighborhoods in Oregon and Washington. Waterfront streets, parks, and low-lying areas that sit just barely above sea level today would find themselves underwater after a rupture. Some permanently. That physical reshaping of the coast is one of the most underreported consequences of a major Cascadia event. Most people think about the shaking. Most people think about the tsunami. The permanent loss of land is something the geological record shows very clearly, and something modern communities above the locked zone are almost entirely unprepared for. Understanding the locked zone is understanding where the energy lives. And the next question is simpler but far more chilling. When did it last break loose, and how do we even know? On January 26, 1700, the ground along the Pacific Northwest coast broke open in one of the most violent earthquakes North America has ever experienced. No seismograph recorded it. No newspaper reported it. Most of the people living near the coast had no written language at all. By every modern standard of documentation, that earthquake should have been lost to history. Scientists found it anyway. The story of how they did it is one of the most remarkable detective cases in geology. It started in the 1980s when researchers began noticing something strange along the coasts of Washington and Oregon. Dead trees. Ancient cedar and spruce trees, still standing upright, rooted in tidal flats and saltwater marshes. Trees do not grow in salt water. For a standing tree to end up rooted in a salt marsh, the land under it had to drop suddenly, letting the ocean swallow the ground the tree was standing on. Those ghost forests became the first clue. Radiocarbon dating of the wood placed the tree's deaths sometime in the late 17th century. That narrowed the window. Scientists then turned to the seafloor. Cores drilled from coastal wetlands and ocean sediments revealed layers of sand embedded in organic mud, a signature pattern left when a tsunami washes inland and deposits beach sand far from the shore. Those tsunami layers matched the same time window as the dead trees. The evidence pointed to a massive earthquake and tsunami sometime around 1700, but scientists needed a precise date, and they found it in the last place anyone expected. Japanese records from early 1700 documented a tsunami that struck the Pacific coast of Japan on January 27th, 1700. The wave was big enough to damage fishing villages and flood coastal areas. What made it remarkable was the absence of any local Japanese earthquake to explain it. Waves that large come from somewhere. Japanese researchers and American geologists working together realized the wave had crossed the entire Pacific Ocean from North America. By measuring the travel time of a tsunami and working backward with ocean models, they pinpointed the source earthquake to the evening of January 26, 1700 Pacific time. With that anchor date, the ghost forests made complete sense. The land had dropped during the earthquake, drowning the trees instantly. The tsunami had raced across the Pacific and struck Japan roughly 9 hours later. The sand layers in the wetland sediment were the tsunami's fingerprint left in the mud. Scientists then refined the magnitude estimate by looking at how far the tsunami had travelled and how powerful the wave was when it reached Japan. The energy required to send a destructive wave across the entire Pacific pointed to a rupture near magnitude 9. A full-length Cascadia break. The detective work did not stop there. Native oral histories from coastal tribes in the Pacific Northwest described a night of catastrophic shaking and flooding, passed down for generations. Some of those accounts described the ground dropping and the ocean rushing inland, matching the geological evidence precisely. What emerged from all of this was a portrait of a disaster that scientists could date to a specific night, estimate in magnitude, and trace across an ocean, without a single instrument having recorded it in real time. That reconstruction also proved something more important. Cascadia had done this before. And the next chapter of that story involves something even harder to picture: what those 5 minutes of shaking would actually do to you. Drive down the Oregon coast toward a place called Nescoin, and you will find something that should not exist. At low tide, when the water pulls back from the beach, dozens of ancient tree stumps emerge from the sand. Blackened, worn smooth by centuries of waves, they jut up from the tidal flats like broken teeth. Scientists have tested the wood. Those trees died over 300 years ago, all at the same time. They were a living forest that the earth swallowed in a single night. Ghost forests like this one run along the Oregon and Washington coast in scattered locations. They are not natural die-offs. They are not disease or drought. They are evidence of one of the most violent geological events in North American history, preserved in wood and sand for anyone willing to look. When the Cascadia Fault broke in 1700, sections of the coastline dropped. In some areas, the ground fell by 3 to 6 feet almost instantly as the locked fault released. A forest standing just above the high tide line found itself suddenly below it. Salt water poured in. Trees cannot survive salt water at their roots. They died where they stood, rooted in place, and the tide came in around them and never fully left. What makes these ghost forests extraordinary as scientific tools is the precision of the information they hold. The outer rings of the wood record the final growing season before the tree died. By matching those rings to known climate patterns and using radiocarbon dating, scientists can narrow down the year of death, and in some cases even the season. The results consistently point to the winter of 1699 to 1700, which aligns exactly with the Japanese tsunami records from January of 1700. The subsidence that killed those trees also left a record in the soil. Beneath the ghost forest stumps, scientists find layers of marsh soil, the organic dark mud that builds up over centuries of plant growth. Above that old soil sits a layer of clean marine sand, the kind that only arrives when a tsunami washes inland. Then, above the sand, a new layer of mud begins, marking the slow return of marsh life after the disaster. That sequence, old soil, tsunami sand, new soil, appears at multiple sites up and down the coast and tells the same story each time. At some locations, there are multiple sequences stacked on top of each other, layer after layer of repeated drops and flooding. Each sequence represents a separate Great Cascadia earthquake from thousands of years past. Scientists have counted these layers and identified at least 19 major ruptures in the last 10,000 years. The ghost forests are the most recent chapter of a very long story. Beyond their scientific value, the ghost forests carry something harder to measure. Standing at Nescoin at low tide, looking at those blackened stumps, you are looking at trees that were alive the night the ground gave way. That forest was a real place. The catastrophe that ended it was real. The same geological system that killed those trees in 1700 is still active, still locked, still loading. The stumps do not move. They just sit there through every tide, proof that the coast has broken before. Across the Pacific, another piece of proof survived in the records of a country that never felt the shaking at all. And that piece of evidence might be the most astonishing part of the entire story. In the winter of 1700, fishing villages on the Pacific coast of Japan began reporting something alarming. The ocean was rising. Waves were pushing far up the shore, flooding fields and damaging coastal structures. People ran. Some boats were lost. The flooding was real and significant. What confused the Japanese was the absence of any warning. A tsunami caused by a local earthquake would have been preceded by shaking. People would have felt the ground move before the water arrived. But on that night, the ground in Japan had stayed completely still. No shaking, no tremor, just the sudden, unexpected arrival of a powerful wave from out at sea. Japanese scholars of the time recorded the event in official documents, merchant logs, and regional histories. They had a term for it, an orphan tsunami, a wave with no parent earthquake to explain it. Those documents survived. and when American and Japanese geologists began collaborating in the 1980s and 1990s to piece together Cascadia's history, those records became one of the most critical pieces of evidence in the entire puzzle. The Japanese records described the wave arriving at multiple coastal locations, with the timing varying based on geography. By comparing those arrival times to known tsunami travel speeds across the Pacific and running ocean models backward, scientists could trace the wave's origin point. Every calculation led to the same place: the fault zone off the coast of Oregon and Washington. From there, the work became even more precise. A tsunami's travel time across an ocean depends on the depth of the water and the distance from the source. The Pacific between Cascadia and Japan is well mapped. Scientists calculated that a wave originating from a full Cascadia rupture would take approximately 9 hours to reach the Japanese coast. The timing in the historical records matched. That 9-hour crossing also carries information about the size of the source earthquake. A small earthquake does not generate a wave powerful enough to cross the Pacific and still damage coastal structures on the other side. The energy required to send a destructive tsunami across the full width of the Pacific pointed to a magnitude 9 or greater rupture. The Orphan tsunami itself became a measuring stick for the earthquake that created it. The collaboration between Japanese and American scientists over this question is one of geology's great cross-cultural achievements. Japanese researchers brought the historical records. American researchers brought the geological field evidence from the ghost forests and coastal sediment layers. Together they built a reconstruction of a disaster that no instrument had ever recorded and that no living witness had survived to document in writing. The date January 26, 1700 became locked in the scientific record. A magnitude 9 rupture along the full length of Cascadia, shaking the Pacific Northwest for minutes, dropping sections of coastline, sending a tsunami across the Pacific, and leaving a fingerprint in the archives of a country 6,000 miles away. That wave tells us something else too. A tsunami powerful enough to damage Japan after crossing the entire Pacific would have been catastrophic at its source. The communities along the Oregon, Washington, and northern California coasts would have faced not just the earthquake, but a wave that arrived while the ground was still shaking. The distance between those two events, the shaking and the flooding, was measured in minutes. And that specific window, how long people have to react after the shaking stops, is something that changes everything about survival. The clock for that begins the moment the fault breaks. Close your eyes for a moment and count to 60. That is 1 minute. Most strong earthquakes last between 10 and 30 seconds. The big ones, the ones that destroy buildings and fill hospital emergency rooms, might last 45 seconds to a full minute. After that, the shaking typically stops. Now count to 65 more times. That is how long a full Cascadia rupture could shake the Pacific Northwest. Up to 5 minutes of continuous, violent ground movement. Scientists who study past megathrust events around the world say that shaking duration is one of the most underestimated factors in earthquake damage, and one of the features that separates a subduction zone rupture from anything most Americans have ever experienced. The reason a Cascadia earthquake lasts so long comes from the size of the fault breaking. In a normal crustal earthquake like those on the San Andreas, the rupture moves fast, travels a limited distance, and ends within seconds to a minute. The energy comes from one concentrated zone and radiates outward quickly. In a megathrust rupture, the fault surface is enormous. A full-length Cascadia break would rupture a zone roughly 600 miles long and perhaps 80 to 100 miles wide. The rupture does not happen all at once. It propagates, spreading along the fault like a crack moving through glass, section by section, for several minutes. During those 5 minutes, the shaking does not stay constant. It rises and falls in intensity as different sections of the fault break. There are bursts of severe motion, brief lulls, then new bursts. The ground does not just shake sideways, it rolls, it heaves vertically. Buildings that survive the first 60 seconds experience continued stress on every joint, every beam, every connection. Structural damage that would have been survivable in a 30-second earthquake becomes catastrophic when the motion continues for 5 minutes. Studies of the 2011 Japan earthquake, which lasted roughly 6 minutes at its peak shaking regions, showed that buildings already weakened by the early phase of shaking were far more vulnerable to the later phases. Engineers described a compounding effect where each additional minute of shaking multiplied the damage from the minutes before it. For people inside buildings during a 5-minute earthquake, the psychological experience is also beyond anything most people can prepare for. Simulations and survivor accounts from long-duration megathrust events consistently describe the same pattern: initial panic, brief hope that it is ending, renewed terror when the shaking intensifies again. The experience of 5 minutes of violent ground movement is fundamentally different from 30 seconds, and the decision-making required in those minutes is severely compromised by terror and physical danger. Emergency planners working on Cascadia scenarios have found that most public understanding of earthquake behaviour is built around the shorter crustal earthquake model. People imagine a jolt, then moving to a doorway, then a few seconds of shaking, then standing up and checking for damage. A 5-minute event does not work that way. The shaking alone can be incapacitating for much of its duration, and the shaking is only the beginning of what a Cascadia rupture produces. What it does to the ground beneath people's feet while it is shaking is something that turns solid cities into something far more frightening than most people have imagined. Seattle and Portland both sit on something that looks like solid ground. Streets, parking lots, parks, building foundations. Everything feels stable. But beneath a surprisingly large portion of both cities, the ground is made of something that behaves very differently when you shake it hard enough and long enough. It is called liquefaction, and it turns solid ground into something closer to quicksand during a major earthquake. To understand how it works, you need to know what is underneath a lot of Pacific Northwest cities. Both Portland and Seattle developed along rivers and bays. Over thousands of years, those waterways deposited layers of loose sand, silt, and gravel. When workers built roads, neighbourhoods, and industrial zones on that material, they were building on sediment that had never been compacted by millions of years of geological pressure. It is loose, it is wet, and it is sitting between the water table and the surface. When an earthquake shakes that saturated, loose material, something remarkable and destructive happens. The sand grains that normally rest against each other and support weight begin to vibrate. The water between the grains gets pressurized. The sand grains effectively start floating in that pressurized water. The ground loses its ability to support anything. For the duration of the shaking, and sometimes well after it stops, that former soil behaves like a thick liquid. Buildings sink, roads buckle. Underground pipes and storage tanks, being lighter than the liquefied soil around them, float upward and break through the surface. Bridges lose their foundation support. In the 2011 Japan earthquake, entire neighbourhoods built on reclaimed land and loose river sediment experienced severe liquefaction. Roads cracked open and sank, buildings tilted at angles, infrastructure that should have survived was destroyed by the ground itself failing rather than the shaking directly. For a 5-minute Cascadia rupture, the liquefaction risk is especially severe. Duration matters enormously for liquefaction. Longer shaking means more cycles of vibration driving that pressure build-up in the saturated soil. Areas that might only partially liquefy in a 30-second earthquake could fully liquefy in a 5-minute one. Seattle has mapped its high-risk zones, large sections of the industrial waterfront, the area around Seattle's port, neighbourhoods built on former tide flats and filled land, and parts of the Duwamish Valley are all identified as having significant liquefaction potential. Portland has similar zones along the Willamette River and in areas of old floodplain fill. Fuel storage facilities, many of which hold the region's petroleum reserves, sit on exactly these kinds of vulnerable soils in both cities. A Cascadia rupture hitting those zones for 5 full minutes would produce ground failure on a scale that goes far beyond broken windows and cracked walls. Storage tanks would rupture and potentially ignite. Underground water mains would fail across wide areas. Bridges crossing rivers on soft sediment would lose their footings. The infrastructure connecting the region, its roads, its fuel, its water, its power grid, would fail in ways that compound every other consequence of the earthquake. Liquefaction is the part of a major earthquake that planners see in their damage models and feel most helpless about. You cannot retrofit soil. You cannot make it stop being loose and saturated. You can only understand where it is and build accordingly, something that was not done for most of the existing infrastructure now sitting on top of it. And the ground failure does not stop there. What the earthquake does to the landscape in another way is something that takes seconds but lasts for generations. Sometime during a full Cascadia rupture, without any additional warning beyond the shaking already underway, sections of the Pacific Northwest coastline will drop. The land will not crack open, it will not explode. It will simply sink permanently by several feet in a matter of seconds. Waterfront neighbourhoods, parks, ports and roads that sit just barely above sea level today will find themselves below it. This is called coseismic subsidence, and the geological record shows it has happened during every major Cascadia rupture in the past. The ghost forests are its most visible proof. Those ancient trees drowned because the land they stood on dropped during the 1700 earthquake. Studies of those forest remains and coastal sediment layers suggest the land fell by 3 to 6 feet in some locations along the Oregon and Washington coast during that event. To understand why the coast drops, you have to go back to the locked zone. The leading edge of North America is being slowly bent downward by the subducting Juan de Fuca plate. That bending means the coastal land is actually being held slightly higher than it would be if the fault were not locked. The plate is dragging it down at depth, but the locked surface is acting like a support that keeps the front edge from dropping all the way. When the fault ruptures and that support releases, the coast rebounds. The inland areas, which were being pushed up, drop back. The offshore areas, which were being pulled down, rise for communities sitting on that coastline. The drop is permanent on any human timescale. The land does not bounce back after the earthquake is over. The new lower elevation becomes the new reality. What was dry land may become intertidal marsh. What was a road just above the waterline may become a shallow bay. Entire sections of modern coastal development in Washington and Oregon sit in zones where past ruptures produced measurable land drops. Scientists studying coastal sediment cores have found that in some locations the subsidence during the 1700 event left a clear boundary layer. Above it, the new mud of a changed coastline. Below it, the old soil of a different landscape. That boundary was not gradual. It was abrupt. The kind of change that happens in seconds. The subsidence also sets up a secondary threat that persists for years and decades after the earthquake itself. Communities that have lost 3 to 5 feet of elevation along the coast become more vulnerable to every future storm surge, every king tide, every normal high water event. The earthquake reshapes the risk landscape permanently, making flooding more likely even from ordinary weather in the years and decades that follow. Modern mapping of Cascadia's coastline has identified the areas at highest subsidence risk, including parts of Seaside and Cannon Beach in Oregon, and low-lying zones along the Washington coast. Emergency planners have started incorporating post-subsidence elevation changes into their disaster models. Some scenarios show that the combination of subsidence and tsunami inundation would affect areas that current flood maps do not flag as high risk. The land will be different after a Cascadia rupture. The coastline will be physically redrawn, and that reorganized coast will face the next threat while the ground is still shaking. Because the tsunami does not wait for the earthquake to end. The shaking has not even stopped yet. The ground is still rolling. Buildings are still cracking. People are still on the floor, hands over their heads, waiting for it to end. And the tsunami is already moving. That is the reality of living on the Cascadia coast. The fault that breaks sits offshore, close enough that the tsunami it generates begins racing toward shore before the earthquake is finished. For many communities along the Oregon and Washington coast, scientists estimate the first waves would arrive in as little as 15 to 30 minutes after the rupture begins. 15 minutes is not much time. It is the length of a short TV show. It is how long it takes most people to walk a mile. It is the time between when your alarm goes off and when you leave the house if you are moving fast. For a coastal family with children, elderly relatives, or physical limitations, 15 minutes to reach high ground can be an impossible ask. The reason the timeline is so short comes from the physics of tsunamis. In deep water, a tsunami travels at speeds close to 500 miles per hour. As it approaches shore and the ocean gets shallower, it slows down but gains height. The wave compresses. By the time it reaches the coastline, it has transformed from an almost invisible ocean disturbance into a wall of water several stories high moving at the speed of a sprinting car. For the Cascadia scenario, the most at-risk communities are the ones sitting on the coast directly above or near the fault zone. Towns like Seaside, Oregon, Westport, Washington, and dozens of smaller coastal communities are within the most vulnerable inundation zones. Models of a full Cascadia tsunami show waves reaching inland by a mile or more in low-lying areas with water heights of 30 feet or higher in some locations. Those numbers come from geological evidence of the 1700 event. Scientists found tsunami sand deposits in coastal wetlands and forests that tell them how far inland the 1700 wave reached and how deep the water was. In some areas, sand from that tsunami appears more than a mile from the modern shoreline. Those same areas are now developed with homes, hotels, schools and roads. Emergency planners have created tsunami hazard maps for all these communities. The maps show clearly which areas would be inundated. They also show, with equal clarity, the problem of getting out. Many coastal Oregon and Washington towns are hemmed in by the ocean on one side and steep terrain on the other. The roads leading to high ground pass through the inundation zone. You have to drive through where the water is going to be in order to get away from it. Some communities have installed tsunami warning sirens. Some have painted blue lines on roads to mark the edges of hazard zones. Some have built evacuation routes with signage pointing toward high ground. These measures save lives. But they depend on people knowing the plan, acting immediately, and having enough time. For communities less than 5 miles from the coast in a low-lying valley or on a beach plain, the 15-minute window requires an almost military-level response. And most of the hundreds of thousands of people living in these zones are not trained for that. Getting people out in time is the coastal challenge, but what the wave itself looks like when it arrives is something that the numbers alone cannot fully capture. The 1700 Cascadia tsunami did not stop at the Oregon coast. It kept going. West across the Pacific, through open ocean, mile after mile, hour after hour. 9 hours after the fault broke off the coast of the Pacific Northwest, that wave reached Japan. 9 hours. The tsunami travelled roughly 5,000 miles across the world's largest ocean, crossed an international date line, and still arrived with enough energy to flood coastal villages, damage buildings, and make it into official historical records. That is the scale of energy a full Cascadia rupture releases into the ocean. To put that in perspective, the wave that hit Japan in 1700 was the leftover energy. It was what remained after the tsunami had already crashed into the Pacific Northwest coast, expended enormous force flooding inland areas, and then continued propagating westward. The destructive power at the source, along the Oregon and Washington coastline, was incomparably greater than what eventually reached Japan. Modern tsunami modelling, using the ocean depth data and fault geometry scientists have mapped in the decades since, allows researchers to simulate what a full Cascadia tsunami would look like in detail. Those models show a complex wave field radiating outward from the rupture zone. The initial wave heading toward the coast arrives in minutes. Secondary and tertiary waves follow at intervals. Hawaii would be impacted within about 5 hours. Japan would face waves again within roughly 9 to 10 hours. Coastal areas in Alaska, British Columbia, and Northern California would all be affected within the first hour. The energy calculations behind a magnitude 9 tsunami are difficult to visualize. Scientists describe the seafloor displacement during a Cascadia rupture as lifting an enormous column of ocean water, possibly the equivalent of filling hundreds of millions of Olympic swimming pools, all lifted simultaneously by several feet. That water has to go somewhere. It goes in every direction. What the 1700 record also tells scientists is something crucial about recurrence. This was a full-length rupture, the entire 600-mile fault breaking at once. The wave it sent across the Pacific was the signature of the whole system failing together. If only part of the fault breaks in the next event, say 200 or 300 miles of it, the tsunami would be smaller. Smaller, but by no means safe. Even a partial Cascadia tsunami would be one of the most serious wave events in American history. The danger for Hawaii and Japan in a future event is real enough that both Pacific warning centers maintain direct communication links to seismic networks along the Cascadia coastline. If sensors detect a major rupture, warnings go out to Pacific nations within minutes. For Hawaii, 5 hours is enough time for most people to evacuate low coastal zones. For Japan, 9 hours is substantial warning time. The countries across the Pacific have more time than the communities sitting directly above the fault. That contrast sits at the center of every Cascadia preparedness conversation. Japan gets 9 hours, Seattle gets 5 minutes, and beneath the earthquake and the tsunami, there is something else scientists have only recently started understanding about the fault itself. Something about its structure that makes the next rupture potentially more complicated and more destructive than the last one. For decades, scientists thought of the Cascadia subduction zone as a single fault, a long continuous boundary where one plate dives under another along one giant surface. The picture was simple. The fault locks. The fault breaks. The coast shakes. The tsunami arrives. The picture is no longer simple. Research published in 2024 by a team at the University of Washington used a new three-dimensional subsurface map of the Cascadia fault zone, built from years of seismic imaging, GPS measurements, and offshore sensor data to reveal something unexpected. The fault is divided into at least 4 major segments. Each segment has its own geometry, its own locking behavior, and potentially its own way of breaking. That discovery changed how scientists think about what the next Cascadia earthquake will actually look like. The 4 segments run roughly north to south along the fault zone. The northernmost sits off the coast of Washington. The next covers northern Oregon. A third runs along central and southern Oregon. And the southernmost reaches into northern California. Each segment has slightly different physical properties. The fault surface dips at a different angle. The rock types along the boundary differ. The degree to which each section is locked appears to vary. Why does that matter? Because those differences affect how a rupture might start, spread, and stop. In a fully unified fault, a rupture that begins in one area propagates continuously along the entire length. In a segmented fault, a rupture might start in one segment and stop at the boundary between segments. Or it might jump the boundary. Or it might trigger rupture in adjacent segments with a short delay. Some of the most important questions in Cascadia science today revolve around exactly these interactions. If only the northern segment breaks, the damage pattern across Washington and British Columbia would be intense, but Oregon and California might receive far less severe shaking. The tsunami generated by a segment rupture would be smaller and more directional than one from a full-length break. But segments can also rupture in sequence. Research on other segmented subduction zones around the world has shown cases where one segment breaks and triggers the next within seconds or minutes, producing what looks from the surface like one continuous giant earthquake. Distinguishing between a single unified rupture and a rapid sequence of segmented breaks requires instruments and analysis that were not available until recent years. The Washington segment carries specific concerns beyond its size. New mapping shows it may be smoother and shallower at certain sections than the segments to its south. Smoother fault surfaces in some geological settings allow rupture to propagate faster and more efficiently. Shallower locking means the energy release is closer to the surface, where it can do more damage to communities above. Scientists are still debating the implications of the segmented model. Some argue the four-segment picture makes worst-case scenarios slightly less likely, because the entire fault may be less likely to break all at once. Others point out that if the segments can trigger each other, a cascade of segment ruptures could produce shaking that lasts even longer than a single unified break. The one thing no scientist disputes is that the segmented model makes Cascadia more complex and harder to predict. The next earthquake may look different from the last one in ways that even the best models cannot fully anticipate. And one specific segment is generating concerns that go far beyond what earlier maps suggested. When researchers at the University of Washington finished their new subsurface map of the Cascadia Fault in 2024, the feature that drew the most urgent attention was not the fault itself. It was what sits above one particular part of it. The Washington segment of Cascadia runs offshore from roughly the Oregon border northward through Puget Sound and into the waters south of British Columbia. Beneath it, the fault geometry appears smoother and shallower than many earlier estimates predicted. The Juan de Fuca plot there dives at an angle that keeps the locked interface relatively close to the surface for a wider horizontal distance than the segments farther south. That geometry has a direct consequence. The zone of strongest shaking during a Washington segment rupture would extend farther inland than it would from a deeper, steeper fault boundary. The shaking intensity at the surface depends not just on the magnitude of the rupture, but on the depth and angle of the fault producing it. A shallower fault surface means more of the energy reaches the ground where people live. Seattle sits roughly above the deeper eastern edge of the Washington segment's locked zone. Portland sits above a similar position relative to the northern Oregon segment. Both cities are built on river deltas, glacial sediments, and old lake bed deposits, the exact kinds of loose, water-saturated ground that amplify earthquake shaking far beyond what bedrock would experience. The amplification effect is significant. When seismic waves travel from solid rock into soft sediment, they slow down and grow taller, the same way an ocean wave grows as it enters shallow water. Studies of basin amplification in Seattle's Puget Sound lowlands and Portland's Willamette Valley suggest that soft sediment zones in those cities could experience shaking 2 to 4 times more intense than the surrounding harder ground. For a 5-minute rupture on the Washington or Northern Oregon segment, that amplification means sustained, intense shaking for soft sediment neighborhoods throughout both metropolitan areas. Seattle's particular geology adds another layer of concern. The city sits in the Puget Sound lowland, a basin filled with glacial debris and sediment left by retreating ice sheets 10,000 years ago. That basin acts like a bowl, trapping and amplifying seismic energy as it arrives. Modelling of Cascadia rupture scenarios for Seattle consistently shows the basin amplification extending the duration and intensity of the most damaging shaking well beyond what would occur outside the city on firmer ground. Portland faces a similar situation in the Willamette Valley. The valley is essentially a broad, flat basin of river sediment. Seismic waves hitting that sediment resonate, bouncing back and forth through the soft material and producing prolonged shaking at damaging frequencies, precisely the frequencies that affect mid-rise concrete and unreinforced masonry buildings. Both cities have large inventories of exactly those building types. Portland in particular has thousands of unreinforced masonry buildings, older brick structures that perform extremely poorly in sustained earthquake shaking. Many were built before any modern seismic codes were adopted. The city has ongoing retrofit programs, but the sheer number of vulnerable buildings makes complete preparation a multi-decade project that is still underway. The combination of fault geometry, basin amplification, building vulnerability, and infrastructure age creates a compounding risk profile for both Seattle and Portland that goes significantly beyond what a simple magnitude estimate would suggest. And deeper underground, something else is happening beneath the Pacific Northwest that scientists have been watching very closely for years. A strange kind of movement that gives no warning and no shaking, but may be telling us something about what is building above it. Every 14 months or so, deep beneath the Pacific Northwest, something remarkable happens. The Cascadia Fault begins to slip. Slowly, silently, for weeks at a time, sections of the plate boundary that are supposed to be locked begin to move. Not with a bang, not with any shaking you could feel standing on the surface. The ground shifts by fractions of an inch over days and weeks, and then the movement stops, and everything goes quiet again. Scientists call these events episodic tremor and slip. Most people have never heard of them, but geologists who study Cascadia consider them one of the most important and puzzling phenomena associated with the fault. Here is what makes them strange. The locked zone, the dangerous upper part of the fault where all the earthquake energy is stored, sits relatively shallow. The episodic tremor and slip events happen deeper, below the locked zone, where the plate is transitioning from locked behaviour to fully sliding behaviour. That transition zone runs roughly 30 to 60 miles underground, well below the zone that would rupture in the main earthquake. When that deeper section slips during an episodic event, it does not relieve stress in the locked zone above it. The movement is happening in a different part of the plate system. But here is the concern that keeps seismologists thinking. When the deep section slips, it subtly changes the stress on the boundary between the deep zone and the locked zone above it. Some researchers have calculated that the slip events slightly increase the stress on the lower edge of the locked zone. Each episode nudges the system a tiny bit closer to failure. The 14-month rhythm of these events was first identified in the early 2000s using a dense network of GPS sensors installed across Oregon and Washington. The sensors were sensitive enough to detect millimeter-scale surface movements, and when scientists looked at years of data, the pattern was unmistakable. Roughly every 14 months, the sensors showed coordinated movement across a wide swath of the Pacific Northwest, the ground shifting slightly as the deep fault zone slipped below. Then it stopped. Then, 14 months later, it happened again. Each episode lasts roughly 2 to 3 weeks. The slip down below is equivalent to a magnitude 7 earthquake in terms of total energy, but because it happens so slowly, it releases no destructive seismic waves. You would not feel it with your body, only with the most sensitive instruments on Earth. Scientists have been watching these events for over 2 decades now. The pattern has remained remarkably regular. The most recent episodes have shown some variations in which sections of the deep zone slip most prominently, and researchers are studying whether those variations say anything about the state of the locked zone above. The honest answer is that nobody is certain. The episodic tremor and slip events might be completely disconnected from the timing of the next major Cascadia rupture, or they might be the deep fault's way of creeping toward a threshold. The instruments keep recording. The pattern keeps repeating. And while scientists are watching the deep fault below, they have also been placing sensors on the ocean floor directly above the locked zone itself, trying to hear whatever that locked surface might be saying before it finally gives way. To understand what a fault is doing before it breaks, you have to get as close to it as possible. For Cascadia, that means going underwater. The locked zone of the Cascadia Fault sits beneath miles of ocean water and hundreds of feet of seafloor sediment. No GPS sensor on land can measure what is happening directly on that buried surface. No seismograph in Seattle tells you the precise state of stress 200 miles offshore and 10 miles underground. To get that data, scientists have spent years placing instruments directly on the ocean floor above the fault. The network is called the Ocean Observatories Initiative, and it includes a set of seafloor cables and instrument arrays anchored to the bottom of the Pacific off the Oregon coast. These instruments measure pressure, seismic motion, temperature, fluid flow and ground tilt, all in real time. All transmitted through fiber optic cables that run back to shore. The data streams continuously, day and night, to research centres where scientists look for patterns in what the fault is doing. What they have found is a complicated picture. The seafloor above the Cascadia locked zone is not perfectly still between major earthquakes. There are slow movements. There are pressure fluctuations. In some areas, fluid seeps upward through the sediment in patterns that change over time. That fluid movement is significant because water on a fault surface reduces friction. When fluids migrate into a locked zone, they can potentially lower the stress threshold needed to trigger a rupture. Recent measurements from the Oregon seafloor network found variations in tilt and pressure that corresponded to the episodic tremor and slip events happening deeper in the fault system, meaning the ocean floor above the fault is physically responding to those deep movements, bending slightly as the deep zone slips, and then returning as the episode ends. That connection between the deep slow slip and the seafloor surface provides a direct measurement of how the two parts of the fault system interact. A separate study published in 2026 used stress testing models combined with years of offshore measurement data to map variability in how different sections of the Cascadia fault respond to the episodic deep slip. The results showed that some sections of the locked zone may be more sensitive to those stress transfers than others. The variability was not random. It correlated with the known segment boundaries identified in the 2024 subsurface mapping work, suggesting the four-segment structure influences not just fault geometry, but also how stress redistributes across the system after every deep slip episode. Researchers are also using the ocean floor instruments to look for longer-term trends. Has the rate of fluid seeping changed over decades? Are certain sections of the seafloor tilting slightly more each year? These are subtle signals, and the record is still relatively short in geological terms, only a few decades of continuous measurement compared to a fault cycle measured in hundreds of years. The honest assessment from researchers working with this data is that the instruments are providing an unprecedented window into a fault system that was previously almost completely invisible. But that window is still new. The patterns emerging from the data require years more of observation before scientists can say confidently what they mean for timing. What the ocean floor sensors have already confirmed is that Cascadia is a dynamic, active and complex system even between its great earthquakes. The fault is doing things constantly. The ground above it is responding. The stress is moving. And while scientists work to interpret those movements offshore, a new concern has emerged on land, one that involves a completely different fault system, hundreds of miles to the south, and the possibility that what happens in one place might trigger something catastrophic somewhere else. For years the models looked reasonable. Scientists estimated where the Juan de Fuca plate was positioned beneath Oregon, drew their hazard maps, and built their shaking predictions based on those estimates. The numbers were not perfect, but they were considered reliable enough to work with. Then a team of researchers took a closer look at the slab beneath northern Oregon, and the numbers changed. A study published in 2025 used new seafloor pressure sensors and seismic imaging to measure the actual depth of the subducting plate beneath the northern Oregon coast more precisely than any previous work had managed. What they found contradicted earlier estimates. The plate there sits shallower than scientists had assumed, shallower by a meaningful amount, enough to matter in every shaking model built for the region. Here is why that matters. The depth of the fault interface controls how seismic energy travels to the surface. A deeper fault sends its energy through more rock before it reaches the ground where people stand. Rock absorbs and scatters some of that energy along the way. A shallower fault delivers its energy through less material. More of it arrives at the surface, and it arrives with less travel distance to spread out and weaken. The northern Oregon coast sits directly above the zone where this newly measured shallow slab runs. Communities like Tillamook, Lincoln City and Newport are positioned above a section of the fault that, according to the new measurements, sits closer to the surface than the previous hazard maps reflected. That means peak shaking in those areas during a Cascadia rupture could be more intense than the maps currently show. The updated geometry also affects the inland reach of strong shaking. When a fault is shallower, the cone of most intense energy radiating upward from the rupture is narrower and more concentrated near the coast. For northern Oregon, that concentration of energy falls on the very coastline where the most tsunami-vulnerable communities are already located. The same towns that have the least time to evacuate before a tsunami arrives would also experience some of the strongest shaking. For engineers and emergency planners, the slab depth revision is the kind of finding that forces a review of every assumption downstream. Building codes for coastal Oregon structures were set using the older depth estimates. Infrastructure design, school construction standards, bridge load tolerances, all of these were calculated with a fault geometry that the new data suggests was off. Revising those standards is a long process. Buildings already standing cannot be redesigned. Bridges already built cannot be moved. What the new measurements do is sharpen the picture of where the risk is highest and make the case for faster action in specific communities. If a school in Lincoln City was built to code in 2010, it was built to a code that did not account for the shallower slab. That school is still standing. The students inside it during the next rupture will depend on a structure designed for a slightly different earthquake than the one that is coming. The Northern Oregon slab discovery also fed directly into new models of how a Cascadia rupture might propagate across the 4 segments identified in 2024. If the Northern Oregon segment sits on a shallower surface, it may behave differently when rupture energy from an adjacent segment arrives at its boundary. It may be easier to rupture. It may contribute more strongly to surface shaking when it does. Scientists are still working through the implications. What the ocean floor told researchers in 2025 is that the fault beneath Oregon is not the fault scientists thought they understood, and that realization connects directly to the ground that Portland and Seattle are actually built on, which turns out to carry its own separate set of problems entirely. Portland began as a trading post on the banks of the Willamette River. Seattle grew up on the shores of Puget Sound. Both cities chose their locations for the same practical reason that most great American cities chose theirs: water access for commerce. Ships could dock, goods could move, people arrived and stayed. What those early settlers did not think about was what was under the ground they were building on. And what is under the ground in both cities is, from an earthquake engineering perspective, deeply problematic. The Willamette Valley that Portland sits in was carved and filled over millions of years by the river itself and by catastrophic Ice Age floods. Roughly 15,000 years ago, a glacial lake in present-day Montana repeatedly broke through its ice dam and sent walls of water racing across the Pacific Northwest. Those floods deposited enormous quantities of loose silt, sand and gravel across the valley floor. Portland then built its downtown, its bridges, its water systems, and its industrial areas on top of that flood deposited material. Seattle's ground story is different, but equally concerning. The lowland areas of the city, including large sections of the industrial district, South Seattle, and waterfront neighborhoods, sit on glacial outwash deposits and tidal flat sediment. After the last ice age, glaciers retreated and left behind loose gravel, sand, and clay. As the city grew in the late 19th and early 20th centuries, significant areas of tidal flat were filled in with whatever material was available, including construction debris and dredge spoil from the harbour. That filled land now holds warehouses, roads, railroad yards, and fuel storage facilities. Both cities also sit within sedimentary basins, geographic bowls where the bedrock dips down and soft material fills the space above it. Those basins trap and amplify seismic energy. When earthquake waves enter a sedimentary basin, they bounce around inside it like sound inside a concert hall, building in intensity and lasting longer than they would over solid rock. Studies of the Seattle Basin, the geological depression beneath the city, show that certain earthquake frequencies could be amplified by a factor of 2 to 4 compared to the surrounding upland areas. For a 5-minute Cascadia rupture, that amplification runs for the full duration of the shaking. A neighbourhood on Seattle's Capitol Hill, sitting on shallow glacial deposits over the basin edge, might experience sustained violent motion for nearly the entire duration of the rupture. A house on bedrock in the nearby foothills might shake severely for the same event, but with noticeably less intensity. That difference in intensity across short distances matters enormously for damage patterns. Emergency responders, hospital capacity, road survivability, and utility infrastructure all concentrate in the urban core, which in both Portland and Seattle sits largely on the soft sediment zones with the highest amplification. Engineers have known about this problem for years. Some progress has been made. Newer buildings in both cities are designed with basin amplification in mind. Retrofit programs have targeted the most vulnerable existing structures, but the inventory of older, vulnerable buildings, particularly older concrete frames and unreinforced brick structures, remains large in both cities. The ground under Portland and Seattle is beautiful, flat, and convenient to build on. It is also some of the most seismically dangerous urban ground in the country. And the buildings sitting on it are only part of the problem. The systems connecting those buildings, the pipelines, the bridges, the roads, the fuel lines, represent a separate and equally serious challenge. Every day, millions of people in the Pacific Northwest use systems they never think about. Water comes out of taps, gas flows into furnaces, bridges hold under tyres, hospitals stay lit. The assumption built into daily life is that all of this continues. After a full Cascadia rupture, most of it stops. The infrastructure of Oregon and Washington was built across several different eras. Much of the critical backbone, the major bridges, the water treatment plants, the large fuel storage terminals, the hospitals and schools, was designed and constructed before scientists fully understood what Cascadia could do. The 1980s was when geologists established that Cascadia was a serious megathrust threat. Most of Portland's and Seattle's major infrastructure had already been built by then, designed to standards that did not account for 5 minutes of magnitude 9 shaking. Water systems are among the most vulnerable. Both Portland and Seattle rely on networks of underground pipes, many of them old cast iron or brittle concrete, to deliver water across their urban areas. Seismic shaking breaks those pipes at joints and weak points. Liquefaction shifts the ground around them, bending and severing lines across wide areas. After the 1994 Northridge earthquake in Los Angeles, a far smaller event than a Cascadia rupture, the water system suffered over 1,000 breaks. Portland's and Seattle's systems face a similar aging pipe inventory with far longer projected shaking duration. Fuel infrastructure is concentrated in exactly the wrong places. The primary petroleum storage facilities for the Pacific Northwest sit along the Duwamish River in Seattle and near the Willamette River in Portland, both on soft sediment and liquefaction-prone ground. Those terminals hold the region's reserves of gasoline, diesel, and aviation fuel. If those tanks fail during the earthquake, through ground failure, rupture, or fire from broken pipelines, the region loses its fuel supply at the exact moment emergency response vehicles need it most. A Federal Emergency Management Agency planning document for a Cascadia scenario estimated fuel supply disruption lasting weeks to months. Bridges are a cascading problem. The Pacific Northwest's geography forces road and rail traffic to cross multiple rivers, bays, and waterways. Many of the bridges doing that work were built before modern seismic design standards existed. Oregon's bridge inventory includes hundreds of older structures rated as seismically vulnerable. Washington's is similar. A Cascadia rupture would close many of those bridges, cutting the region into isolated pockets separated by water with no way across. Emergency vehicles, supply trucks, and evacuation routes all depend on those crossings. Hospitals present their own specific failure mode. A hospital needs to function precisely when everything else is failing. But most older hospital buildings in the region were not designed for the combined effects of long-duration shaking, potential liquefaction, and loss of utilities. A facility that suffers structural damage, loses water pressure, loses backup generator fuel, and cannot be reached by patients or staff because the roads are blocked has ceased to function as a hospital at the worst possible moment. The Oregon Resilience Plan, a major study completed for the Oregon legislature, concluded that after a full Cascadia rupture, the southern coast could be isolated for weeks, the northern coast for months, Major transportation routes could take months to a year to restore. Full regional recovery could take years to decades. Those projections are sobering. But the Pacific Northwest does not face only one earthquake threat. A different kind of fault, running through California, operates on its own schedule, with its own destructive potential and a different but equally alarming set of consequences. While Cascadia loads up in silence offshore, California has been living with a different earthquake machine for as long as people have been keeping records. The San Andreas fault system does not hide. It runs across the landscape in visible ridges, offset streams, and long narrow valleys that mark its path through the state. From the Salton Sea in the south to the wine country north of San Francisco, the San Andreas and its related faults thread through some of the most densely populated land in the country. The San Andreas is a strike-slip fault, which means the plates on either side of it move horizontally past each other. The Pacific Plate, carrying Los Angeles and much of coastal California, slowly moves northwest relative to the North American Plate, which holds the rest of the continent. The average movement is roughly 2 inches per year. At that rate, in about 15 million years, Los Angeles will sit roughly where San Francisco is today. That horizontal sliding produces a fundamentally different kind of earthquake from a megathrust like Cascadia. The rupture zone is narrower. The fault runs through land rather than underwater, so it generates no tsunami in most scenarios. The shaking, while violent, typically lasts tens of seconds to a couple of minutes rather than 5, and the fault relieves stress in segments more regularly, producing a steady background of smaller earthquakes that keep the system partially vented. But regular small activity does not mean the San Andreas is safe. Several sections of the fault have not produced a major rupture in a very long time. The southern San Andreas, the stretch that runs near the greater Los Angeles area, last broke in a major event in 1757. That is over 250 years of stress accumulation on a fault segment capable of producing a magnitude 8 earthquake. Scientists have measured the accumulated motion along that locked southern section and concluded that the region is significantly overdue for a large rupture. A major southern San Andreas earthquake would affect one of the largest metropolitan areas in the United States. Greater Los Angeles holds roughly 13 million people. The shaking from a magnitude 8 rupture on the southern San Andreas would be severe across a wide area. The Los Angeles basin, like Seattle and Portland, sits on soft sediment that amplifies shaking. Millions of older buildings, including tens of thousands of soft-story apartment buildings that have already been identified as dangerous in earthquakes, stand in the projected shaking zone. Beyond Los Angeles, the San Andreas system includes parallel and branching faults running through the Bay Area, including the Hayward Fault, which runs directly beneath Oakland and several East Bay communities. A major Hayward earthquake would affect the densely populated eastern shore of San Francisco Bay. Scientists consider the Hayward one of the most dangerous urban faults in the country, based on the combination of its rupture potential and the density of population directly above it. California's earthquake clocks are running on their own schedules, independent of Cascadia's. For years, scientists treated them as separate problems. Then a discovery buried in ocean sediment changed that assumption entirely and raised a question that no one had seriously considered before. The two fault systems sit hundreds of miles apart. One is underwater and produces megathrust earthquakes. The other runs through land and produces strike-slip earthquakes. On the surface, they seem entirely separate. Scientists studying one did not typically worry much about what the other was doing. Then a team of geologists started pulling cores from the ocean floor near the Northern California coast, and what they found in the sediment layers upended that comfortable separation. The ocean floor off the coast of Northern California sits at the southern end of the Cascadia subduction zone, near the point where the Juan de Fuca Plate ends and the San Andreas system begins. Sediment accumulates on that seafloor over thousands of years, building up in layers. Those layers record events. Earthquakes disturb the sediment and leave turbidite deposits. Dense layers of sand and siltbat settle out of the water column after a submarine landslide triggered by shaking. Each major earthquake produces a recognizable signature layer. When scientists analyzed those sediment cores, they found something that stopped them. The turbidite layers from large Cascadia earthquakes and the turbidite layers from large northern San Andreas earthquakes were paired. In layer after layer going back 3,000 years, a Cascadia event and a San Andreas event appeared in the sediment record within a very short time of each other, sometimes so close together that the layers were nearly indistinguishable. The researchers counted up to 8 of these earthquake pairs in the record. 8 times in the last 3,000 years, a major Cascadia rupture and a major northern San Andreas rupture appear to have occurred within minutes or hours of each other. The physical mechanism proposed to explain this pairing is seismic triggering. When a massive fault breaks, it sends seismic waves radiating outward in all directions. Those waves travel through the crust and can reach other faults hundreds of miles away. If a distant fault is already near its own breaking point, the extra stress added by incoming seismic waves can push it past the threshold and trigger its own rupture. This kind of dynamic triggering has been documented in smaller events globally, where one earthquake sets off another at distances that seem too far for the faults to be directly connected. In the Cascadia and San Andreas case, the two fault systems are not directly connected, but they are close enough for seismic waves from a Cascadia magnitude 9 to reach the northern San Andreas in minutes. If the northern San Andreas is in a late stage of its own stress cycle, that additional energy could be enough to trigger it. The research team was careful to frame this as a pattern in the geological record that requires more study before its mechanics are fully understood. Scientists do not claim this pairing happens every time Cascadia breaks, and they emphasize that predicting it in advance is currently impossible. But 8 paired events in 3,000 years of record is a pattern that cannot be dismissed. If the pattern is real, then the worst West Coast earthquake scenario is not one disaster. It is 2, arriving almost simultaneously across a region stretching from British Columbia to Los Angeles. Picture the Pacific Northwest in the minutes after a full Cascadia rupture. The ground has shaken for 5 minutes. Coastal communities are evacuating toward high ground. Emergency services are overwhelmed before they have even begun assessing damage. Power is out across wide areas, bridges are closed, the tsunami is already on its way. Now picture that while all of that is unfolding, the northern San Andreas, hundreds of miles to the south, breaks. A major earthquake along the northern San Andreas would send violent shaking through the San Francisco Bay Area. Buildings already weakened by decades of deferred maintenance and earlier smaller quakes would fail. Fires would start as they did after the 1906 San Francisco earthquake, when broken gas lines and downed electrical infrastructure ignite and spread without working water pressure to stop them. The region's hospitals, emergency services and transportation networks would be overwhelmed by their own local disaster. 2 of the major population centres on the West Coast would be in simultaneous crisis. The National Guard, Federal Emergency Management Agency, and every federal disaster resource would face requests from multiple catastrophic events at the same time, in the same general region, across a stretch of the country roughly 1,000 miles long. Resources would have to be divided, prioritised and rationed. The response to each individual disaster would be slower and less complete because of the demands from the other. The infrastructure connection between Northern California and the Pacific Northwest would also compound the problem. Major highways, railroads and supply chains run the length of the West Coast. Fuel, food and emergency supplies for the Pacific Northwest often route through California distribution centres. If California is simultaneously managing its own major disaster, those supply lines collapse from both ends. Port access is a related concern. The West Coast ports handle an enormous share of American trade. Seattle, Portland, Oakland and Los Angeles all move goods in and out of the country continuously. A simultaneous major earthquake scenario affecting multiple ports could disrupt national supply chains for consumer goods, industrial materials and food products. The effects would extend well beyond the West Coast. The compounding of 2 disasters also creates a human crisis that goes beyond logistics. emergency mental health resources, search and rescue teams, medical specialists and structural engineers are finite. Training exercises for Cascadia response have already shown that the Pacific Northwest alone would overwhelm existing response capacity. Adding a simultaneous Bay Area disaster to that picture multiplies the gap between what is needed and what is available. Scientists cannot say when this scenario will happen, or whether the pairing mechanism is reliable enough to expect it in the next major event. The sediment record shows it has happened before. The geological conditions that enabled those past pairings still exist. The San Andreas in its northern section is loaded. Cascadia is loaded. Whether they break together or separately, and when, remains beyond anyone's ability to forecast. What scientists can say, and have said repeatedly in public reports, is that planning only for each disaster in isolation understates the actual risk the West Coast faces. The paired scenario needs to be part of the conversation, even if its probability in any given event remains uncertain. And behind the uncertainty about when and how, there is a number that puts the whole picture in sharp focus. The answer to questions about Cascadia's past does not come from laboratory instruments or computer models alone. It comes from mud, specifically from the layers of material that have settled on the ocean floor and in coastal wetlands over thousands of years, slowly building a record of every major earthquake the fault has produced. Scientists call this kind of geological detective work Paleoseismology. It is the study of ancient earthquakes through the traces they leave in the landscape. For Cascadia, the most important evidence comes from two sources: turbidite cores pulled from the deep ocean floor and sediment cores collected from coastal marshes. Offshore, when a major Cascadia earthquake shakes the seafloor, it triggers underwater landslides along the continental slope. Those slides send clouds of sediment cascading down into the deep ocean basin, where the material settles out in a distinctive layer called a turbidite. Each turbidite looks different from the normal fine-grained sediment accumulating between earthquakes. It is coarser, denser, and sharply bounded. Scientists can identify individual turbidite layers and date them using radiocarbon methods applied to organic material within the sediment. Multiple cores collected from different canyons along the Cascadia margin have been compared. The turbidite layers in different cores match each other in age, which confirms they came from a single earthquake powerful enough to trigger landslides across a wide area simultaneously. A localized event would only appear in one canyon's sediment, not in cores from canyons hundreds of miles apart. That matching across multiple cores has allowed scientists to count and date past Cascadia earthquakes going back roughly 10,000 years. The record shows at least 19 major ruptures over that period. The spacing between events is not uniform. Some intervals were longer than 500 years, some were shorter than 300 years. The average for full-length ruptures across the whole fault sits somewhere around 500 years. The current gap since 1700 is over 300 years and growing. Coastal marsh cores add a complementary layer of evidence. In those cores, the earthquake signature appears differently, a sudden change from organic marsh sediment to marine sand. The Tsunami deposit, followed by a layer showing that the land dropped abruptly. In some cores, that drop shows up as an overnight change from freshwater marsh to saltwater conditions. Exactly what would happen if the land sank several feet and the tides reclaimed the area. The paired offshore and onshore records have allowed researchers to build a remarkably detailed earthquake history for a fault that produced no written records until 300 years ago. That history is what feeds directly into modern probability estimates. The current best estimate from the United States Geological Survey puts the chance of a roughly magnitude 9 full-length Cascadia rupture at 10 to 15% in the next 50 years. A slightly smaller but still major rupture from one or more segments carries higher odds. Those probabilities are built directly on the counted intervals in the sediment record, combined with measurements of how much strain is currently stored in the locked zone. 10 to 15% sounds manageable until you think about it in context. If your doctor told you there was a 15% chance of a serious health event in the next 50 years, you would change your behaviour. You would get checkups. You would reduce risk factors. You would plan. The sediment record has given scientists the data to issue exactly that kind of warning for the Pacific Northwest. The question is what gets built in response to that warning. 10 to 15%. The United States Geological Survey updated that number in 2025. That is the estimated probability of a roughly magnitude 9 Cascadia earthquake in the next 50 years. A partial rupture of one or more segments carries a higher chance of occurring sooner. The numbers reflect the combined weight of the sediment record, the GP's strain data, and the offshore measurements. Numbers like these can feel abstract. 15% sounds low compared to flipping a coin. But consider how societies respond to other 15% risks. Aviation safety systems are designed around failure probabilities far lower than 1%. Nuclear plants run extensive backup systems for events with probabilities in the fractions of a single percent. The safety systems around everyday products from car brakes to medical devices are engineered for risks that, expressed as annual probabilities, are nearly invisible. A 15% chance over 50 years translates to roughly a 1 in 300 chance in any given year. That sounds small. But the Pacific Northwest is not playing this lottery once. It plays it every year. And the consequences of the losing number are not a minor inconvenience. They are, according to every major modelling study, the largest natural disaster in the history of the United States. Federal Emergency Management Agency planning documents for the Cascadia scenario describe outcomes that are difficult to absorb. Tens of thousands of casualties in the immediate event. Over 1 million people displaced from their homes. The southern Oregon coast potentially isolated for weeks. Infrastructure recovery timelines measured in months for transportation and years for some utility systems. Total economic losses that could exceed the gross domestic product of many countries. Against that backdrop, the 15% probability is not a reassurance. It is a deadline of unknown length. The uncertainty about whether the rupture is 30 years away or 300 years away does not change the physical reality of what is stored in the fault. The energy is there. The locked zone is compressed. The plates are pressing. What the probability does is give planners a framework for action. It says this event is real. It is within a foreseeable human timescale, and preparation now makes a measurable difference to outcomes later. Studies of earthquake preparedness consistently show that investment made before a disaster saves multiple times its value in reduced casualties and faster recovery. Japan spent decades after the 1995 Kobe earthquake systematically retrofitting buildings, strengthening infrastructure, and training coastal communities. When the 2011 earthquake and tsunami struck, the death toll, while catastrophic, was significantly lower than comparable events would have produced on less prepared coastlines. The Pacific Northwest has made meaningful progress in some areas. Building codes have been updated. Tsunami evacuation routes have been marked. Warning systems have been installed. Retrofit programs are underway. But the scale of preparation still falls short of the scale of the threat as described in the Geological Survey's own planning documents. The 15% probability sits in every planning meeting, every budget discussion, every retrofit proposal in the Pacific Northwest. Some of what has been built in response to it is impressive. Some of it is deeply insufficient. And one training exercise conducted years ago made the gap between preparation and reality impossible to ignore. In 2016, emergency managers across the Pacific Northwest ran the largest earthquake preparedness exercise in the region's history. They called it Cascadia Rising. Over 50 agencies participated: federal, state, county, and local. Military units were involved. National Guard resources were deployed. The exercise simulated a full magnitude 9 Cascadia rupture and tested how the response system would hold up. The results were sobering. Within the first simulated hours, the exercise exposed the same bottleneck in nearly every scenario: communication failure. The shaking in the model took down cell towers, damaged repeater stations, and severed fibre lines. Emergency coordinators could not reach each other. Agencies trying to organise response could not determine which roads were passable, which hospitals were functional, or where the highest concentrations of casualties were located. Decision makers were operating on guesswork for the first critical hours. Transportation collapse came second. In the exercise models, the major bridges across the Columbia River, the main link between Oregon and Washington, suffered damage severe enough to close multiple crossings. Highway 1 on the coast, the primary route running through the tsunami zone, was washed out in multiple locations. Supply convoys from unaffected inland areas could not reach the coast because the roads that connected them no longer existed. Medical response ran into its own wall. The exercise projected tens of thousands of people needing immediate medical attention within the first 24 hours. The hospital capacity across Oregon and Washington, even assuming every facility survived fully intact, was far below that number. Field hospitals would need to be erected and staffed quickly, requiring supplies and personnel that would themselves need to be transported over damaged infrastructure. Coordination between agencies proved harder in practice than on paper. Different agencies used different communication systems, different terminology, and different command structures. Information that one agency had could not reach another quickly because the systems they each relied on were incompatible or damaged. The exercise identified this as a critical vulnerability that required expensive system upgrades and extensive cross-agency training to address. Perhaps the most pointed finding from Cascadia Rising was the timeline for recovery. Exercise planners modelled how long it would take to restore basic services to the southern Oregon coast under realistic resource constraints. The results showed that some areas could wait weeks for road access. Fuel and food resupply might take months to regularise. Full restoration of water and power systems could stretch a year or more in the hardest hit areas. These findings were not hidden. They were published in detailed after-action reports available to state legislatures, federal agencies, and the public. They identified specific gaps and made specific recommendations. The years since 2016 have seen some of those recommendations acted on, and others stalled by funding limits and competing priorities. What Cascadia Rising did permanently was establish a documented baseline for what the response system could and could not do. It made the abstract threat concrete. And it directed attention toward a country that had already faced a comparable disaster and rebuilt its response systems from the ground up. At 2:46 in the afternoon on March 11th, 2011, a magnitude 9 earthquake struck off the northeastern coast of Japan. The shaking lasted approximately 6 minutes. The tsunami that followed reached heights of over 100 feet in some locations. Nearly 20,000 people died. Over 300,000 were displaced. The damage to infrastructure, industry, and communities reshaped entire sections of the Japanese coastline. Japan's response over the following decade became a case study in how a society rebuilds not just physically, but conceptually after a catastrophic event. The seawall construction program Japan launched after 2011 is one of the largest civil engineering projects in modern history. Hundreds of miles of coastal barriers were raised or newly built along the Tohoku coastline. In some communities, the walls stand nearly 40 feet high. Engineers designed them to stop or significantly reduce the most likely future tsunami wave heights based on the geological record of past events along that coast. The walls are not universally loved. Some coastal towns feel they block the view and disconnect communities from the sea that defined their economies and culture. But they represent a physical commitment to reducing future casualties at a scale few other countries have matched. Beyond seawalls, Japan rebuilt its coastal communities with vertical evacuation in mind. Tsunami evacuation towers, concrete structures with open staircases designed to hold hundreds of people, were constructed in communities where reaching high ground by land was too slow given the expected warning times. Evacuation routes were repaved, widened, and lit. Signage was standardized across the country. Schools began running regular evacuation drills that included timed practice walks to high ground. Japan also invested heavily in its earthquake early warning system. The country already had an extensive seismograph network, but after 2011, the offshore monitoring was expanded. New pressure sensors were placed on the seafloor to detect the moment of rupture and transmit data to shore in seconds. The goal was to extend warning time even by a few seconds, because seconds translate directly into lives in a tsunami scenario. The Pacific Northwest has adopted some of these lessons. Vertical evacuation towers have been built in communities on the Washington and Oregon coast. The Shake Alert early warning system, developed jointly by the United States Geological Survey and several universities, is operational across California, Oregon, and Washington. Tsunami signage has been standardized in most coastal communities. The gap between Japan's post-2011 investment and what the Pacific Northwest has built is partly a matter of timing and partly a matter of resources. Japan faced its disaster and rebuilt in response to lived experience. The Pacific Northwest is trying to prepare in advance of an event that most residents have never personally experienced. Maintaining urgency and funding for a disaster that has not happened yet is a persistent challenge for every community in the Cascadia zone. What Japan's example makes undeniably clear is that the preparation gap can be closed. The tools exist. The engineering is understood. The question is whether the investment happens before the rupture or in the painful rebuilding afterward. On the coast of Washington, in a small community called Acosta, there is a building that does not look like much from the outside. It is a concrete structure attached to the local elementary school, rising several stories above the flat coastal plain. It has open metal staircases on the outside, leading to a rooftop platform large enough to hold hundreds of people. It looks industrial, utilitarian, almost out of place beside the wooden school building next to it. That structure is designed to save everyone inside it when the tsunami arrives. Acosta Elementary School sits in a location with no realistic path to high ground in the time a Cascadia tsunami would allow. The nearest elevated terrain is too far. The roads leading away from the coast pass through the inundation zone. When planners looked at the evacuation math for Acosta, they concluded that horizontal evacuation, the standard approach of driving or running to high ground, would leave most of the school's students and staff in the path of the wave. The solution was vertical evacuation. Build up instead of running out. The rooftop platform sits high enough above sea level that tsunami models suggest it would remain above the water even in a full Cascadia event. Enough food, water, and medical supplies are stored there to sustain hundreds of people for days while the water recedes and rescue operations can reach the community. Acosta's tower was the first tsunami vertical evacuation structure built at a school in the continental United States. It opened in 2016 and immediately became a model for other coastal communities facing the same impossible evacuation math. Similar structures have since been built or approved in Westport, Washington, and in several Oregon coastal communities. Each one represents a local community making a clear-eyed decision about its geography and building accordingly. The towers acknowledge what the maps show: some places cannot get everyone out in time by any road, and the honest response to that reality is to build refuges rather than pretend horizontal evacuation is sufficient everywhere. The towers also raise a harder question about the communities that do not have them yet. Dozens of coastal towns along the Oregon and Washington coast sit in similar geographic situations. Schools, nursing homes, hotels, and residential neighborhoods full of elderly or mobility-limited residents face the same evacuation math as Acosta did. Not all of them have the funding or the political will to build vertical evacuation structures. The cost of a vertical evacuation tower varies based on size and site conditions, but typically runs into the millions of dollars for a structure capable of holding several hundred people. For small coastal communities with limited tax bases, that cost is significant. State and federal funding programs exist to support construction, but demand outpaces available funding. emergency managers working in coastal communities have described the towers as one of the most effective per-dollar investments in tsunami preparedness available. A single tower protects a fixed point, but does so with near certainty. A community with multiple towers distributed across its inundation zone achieves something that no amount of signage or drills alone can fully provide: a physical guarantee of safety for people who cannot reach high ground in time. The towers stand as a concrete statement that the threat is real and the community has decided to face it honestly. But even a network of towers depends on people knowing the rupture has happened, and the system built to deliver that warning operates on a timeline that might surprise you. When the Cascadia fault finally breaks, seismographs across the Pacific Northwest will detect it within seconds. The seismic waves radiating outward from the rupture travel through the crust at roughly 3 to 5 miles per second. Before those waves reach Portland or Seattle, sensors closer to the fault will have already recorded the event, identified it as a major earthquake, and sent an alert through the Shake Alert system. Shake Alert is the earthquake early warning system now operating across California, Oregon, and Washington. It uses a dense network of seismographs to detect and characterize earthquakes in real time, then sends alerts to phones, emergency systems, and automated industrial controls before the shaking arrives at more distant locations. The system is real, it is operational, and in the right circumstances it saves lives. The amount of warning it can provide depends almost entirely on where you are standing relative to the earthquake's epicenter. For a Cascadia rupture centered offshore, the fault is closest to the coast. Communities sitting directly above the locked zone near the Oregon and Washington shoreline would receive essentially no meaningful warning. The seismic waves and the Shake Alert notification would arrive nearly simultaneously, or the waves might arrive first. For Seattle, which sits roughly 100 miles from the offshore fault zone, Shake Alert could potentially deliver 15 to 45 seconds of warning before intense shaking begins. For Portland, similar distances produce similar windows. 15 to 45 seconds is not enough time to evacuate a building. It is not enough time to drive away from a dangerous structure or reach open ground. What it is enough time for is specific, targeted, automated responses that save lives without requiring any human decision. 15 seconds of warning can stop trains before they reach switches or bridges, preventing derailments. It can slow down surgical robots and pause certain medical procedures before shaking disrupts them. It can trigger automatic shutdown of industrial processes at chemical plants and refineries that become dangerous when shaken unexpectedly. It can open fire station bay doors so that shaking does not trap trucks inside. It can send an alert to your phone so you can drop under a desk rather than remain standing in a doorway when the shaking begins. Those automated responses and those seconds of personal warning translate into measurable reductions in casualties and secondary disasters, even when the primary shaking cannot be avoided. Japan's early warning system, far more mature than Shake Alert and with a much denser sensor network, has demonstrated this repeatedly. Warning issued seconds before shaking allows people to brace, get away from windows, and move away from heavy objects that could fall on them. Shake Alert has been tested against historical earthquake data for the region and has performed well in those simulations. For a Cascadia scale event, it would also rapidly trigger coordination among emergency services, alerting fire departments, hospitals, and utility operators simultaneously rather than waiting for the shaking to stop and human reporting to begin. The system continues to expand. More sensors are being added to improve detection speed and coverage. Integration with wireless emergency alerts, the same system that sends amber alerts to phones, means that almost every cell phone in the affected area would receive a notification within seconds of the system's detection. Seconds matter in an earthquake. Shake Alert is a tool that turns those seconds into action. But the deeper question about Cascadia, the one that shapes every damage model and every response plan, comes down to something scientists still cannot answer with certainty. And that single unknown carries more consequences than almost any other variable in the entire picture. Before the 2004 Indian Ocean earthquake, which sent a tsunami killing over 200,000 people across 14 countries. Something unusual was reported at wildlife preserves and coastal areas across the region. Elephants moved to higher ground hours before the waves arrived. Flamingos abandoned low-lying nesting areas. Dogs refused to go to the beach. Captive animals at Sri Lankan reserves became agitated and moved away from the coast well before any human-detectable warning existed. These accounts circulated widely after the disaster and sparked serious scientific interest in whether animals could detect earthquake or tsunami precursors ahead of human instruments. Researchers began reviewing records from past major earthquakes, looking for documented animal behavioural changes that preceded the events. What they found was tantalising but inconsistent. Some studies found credible accounts of unusual animal behaviour before major ruptures. Others found no pattern at all. The challenge with animal behaviour as a warning signal is that animals respond to countless stimuli. An elephant moving uphill might be responding to infrasound from an approaching earthquake, or it might be responding to a change in wind, a distant predator, or a behaviour pattern unrelated to geology entirely. Distinguishing earthquake-relevant behaviour from normal animal activity requires a level of controlled observation that is extremely difficult in wild populations. The most carefully documented cases involve sensitivity to infrasound and ground vibration. Some species can detect frequencies well below the range of human hearing. The P waves that precede destructive S waves in an earthquake travel faster and arrive earlier. Some animals may be responding to those initial milder wave arrivals before the damaging motion begins. If that is the mechanism, it would give animals at most a few extra seconds of warning over human perception, useful for a sprinting animal but not practically useful for evacuation planning. Science has largely moved past relying on animal behaviour as a systematic warning tool and toward the ocean floor sensor networks described earlier. Those sensors, however, are designed to measure what the fault is doing between major events. For the seconds to minutes warning window when an earthquake is actually beginning, the relevant instruments are the seismographs feeding shake alert. One category of ocean sensor does play a direct role in tsunami warning. Pressure sensors called Deep Ocean Assessment and Reporting of Tsunamis buoys are anchored at depth across the Pacific. They measure water pressure changes at the seafloor, which reflect the passage of a tsunami wave overhead. When a buoy detects the pressure signature of a tsunami, it transmits that data via satellite to warning centres in real time. The network allows the Pacific Tsunami Warning Centre to confirm a tsunami is actually propagating within minutes of a major earthquake, dramatically improving the reliability of coastal warnings compared to earthquake-only detection. For coastal communities on the Cascadia shoreline, those buoys provide confirmation rather than early warning. The wave is already moving when the buoy data arrives. For Hawaii and Japan, the buoy network provides critical lead time for evacuation. For a family standing on an Oregon beach when Cascadia breaks, the warning is simply the shaking itself. Every preparedness guide for the Pacific Northwest delivers the same message: if you are on the coast and the ground shakes hard, move to high ground immediately and do not wait for an official warning. The shaking is the warning. The science of detecting what the fault does before it breaks is evolving rapidly. New instruments are being placed, new analytical methods are being developed, and one question sits above all others in the minds of researchers who have spent their careers studying this fault. Every model, every simulation, every probability estimate for Cascadia depends on one variable that no scientist can currently determine. Will the next rupture break the entire 600-mile fault at once, or will it break only part of it? That single question changes the scale of the disaster more than almost any other factor. A full-length rupture, all 4 segments breaking in sequence within seconds or minutes of each other, would produce a magnitude 9 or larger earthquake. It would generate the largest tsunami in the recorded history of North America. It would shake the Pacific Northwest for close to 5 minutes. It would be the event every planning document has been trying to prepare for. The death toll in a full rupture scenario, assuming current population and current infrastructure, has been modelled at tens of thousands in the immediate period. with total casualties and displaced persons in the hundreds of thousands. A partial rupture, one or two segments breaking while others hold, would produce a significantly smaller earthquake, perhaps magnitude 7.5 to 8.3, depending on which segments break and how much of each one ruptures. It would produce a smaller tsunami. It would cause severe damage in some areas and minimal damage in others. It would be a major disaster. It would also be survivable at a regional level in ways that a full rupture would not be. The challenge for scientists is that the physical difference between the two scenarios lies in what happens at the segment boundaries. When rupture energy reaches the junction between two segments, several things can happen. The energy can propagate through if the boundary is weak enough. It can reflect back if the boundary is strong. It can slow and then jump the boundary after a delay. The outcome depends on detailed properties of the rock, the fluid content, the roughness of the fault surface, and the stress state at the boundary, none of which can be measured directly from the surface. New models published in 2026 from a University of Washington team used stress testing across the known segment boundaries to try to estimate which configurations are most likely. Their results suggested significant variability. Some boundary configurations would likely stop a rupture after one or two segments. Others would allow propagation across the full fault length. The physical conditions at those boundaries today are not fully known, which means the models produce a range of possible outcomes rather than a single prediction. That range frustrates planners who need to design for a specific scenario. Engineering a bridge to survive a magnitude 8 is a different specification than engineering it for a magnitude 9. Designing hospital backup power systems for 3 days of isolation is different from designing for 3 months. Every preparedness investment involves implicit assumptions about the scale of the event, and the scale remains genuinely uncertain. Scientists working on this problem are clear about the limits of current knowledge. The instruments to resolve this question exist, or are being developed, but the data required to feed them accurately takes decades of observation. The locked zone is not transparent, the segment boundaries are not labelled. The fault is doing whatever it is doing dozens of miles underground and beneath miles of ocean, and it is not yet speaking clearly enough for researchers to hear it fully. What is certain is that both scenarios, full rupture and partial rupture, are realistic possibilities. Both are within the range the geological record supports. And the next chapter of this story will be written by the fault itself, on a timeline that no human instrument can currently predict. Knowing the threat exists is one thing. Deciding what to do about it is another. For the millions of people living in the Pacific Northwest, the gap between understanding Cascadia and actually preparing for it is where most of the work still needs to happen. Emergency management agencies in Oregon and Washington have published straightforward guidance based on the science. The basics are consistent across every credible preparedness document. Store enough water for each person in your household for at least 2 weeks, roughly a gallon per day. Keep enough food to last 2 weeks without electricity or refrigeration. Maintain a supply of prescription medications, since distribution systems for medicine would be severely disrupted after a major rupture. Keep a battery-powered or hand-crank radio, because it would likely be the only working information source in the immediate aftermath when cell networks are down. These are the basics. They address the period immediately following the rupture, when supply chains are broken, stores are closed, and emergency services are overwhelmed with the most urgent cases. Households that can sustain themselves for 2 weeks place far less demand on a response system already stretched beyond capacity. Every family that prepares independently reduces the burden on rescue operations, trying to reach the people who had no options. For coastal residents, the additional layer of preparation is knowing the local tsunami hazard zone and the evacuation route out of it. Most Pacific Northwest coastal communities have published hazard maps. Blue lines or signs on roads mark the zone boundaries. Knowing whether your home, school, or workplace sits inside the inundation zone, and knowing the fastest route out, is the difference between a decision made in advance and a decision made in terror during the first 60 seconds of shaking. The rule for coastal communities is universal and simple. If the ground shakes violently, move immediately to high ground or a vertical evacuation structure. Do not wait for a siren. Do not wait for an official announcement. The shaking is the warning. Sirens may not work. Communications may be down. The window is measured in minutes. Beyond individual preparation, community-level actions matter. Supporting retrofit programs for older school buildings and hospitals extends protection to people who have no individual choice about the structure they are in. Advocating for vertical evacuation towers in vulnerable coastal communities creates options for people who cannot evacuate horizontally in time. Engaging with local emergency management planning ensures that the people closest to the problem have the resources to address it. Japan's post-2011 transformation demonstrated that community-scale preparation, widely practiced and regularly rehearsed, changes outcomes dramatically. The survival rates in communities that had rehearsed tsunami evacuation before 2011 were measurably higher than in communities that had not. Preparation is not a guarantee, but it is the most powerful variable individuals and communities can actually control. The science has done its part. The sediment cores have been pulled. The GPS sensors are running. The fault has been mapped in 3 dimensions. The probability has been estimated. The planning scenarios have been modelled and published. What remains is the translation of that knowledge into individual choices, community investments, and policy decisions made before the ground begins to move. 326 years have passed since the last great Cascadia earthquake. The coast has grown. Cities have been built. Highways were cut through forests that did not exist when the fault last broke. Millions of people have made their lives in the most beautiful and productive corner of the Pacific Northwest, mostly without thinking too hard about what sits offshore beneath the ocean. The fault has not forgotten any of them. Everything the science has revealed points to the same conclusion. The Juan de Fuca plate is still pressing, the locked zone is still loaded, the GPS sensors are still recording compression, the ghost forests are still standing in the tidal flats at Nescoin, blackened and silent. The most patient reminder on the continent that this has happened before and will happen again. What the geological record cannot tell us is when. The sediment cores have shown intervals as short as 200 years and as long as over 1,000 years between full-length ruptures. The current interval is over 300 years. That places it within the known range of recurrence, on the early to middle part of the distribution, not overdue in any alarming statistical sense, but fully within the window where the next rupture becomes increasingly possible with each passing decade. The uncertainties that remain are real and significant. Scientists do not know whether the next event will break the whole fault or just part of it. They do not know whether the 4 segments will rupture together or in sequence. They do not know whether a Cascadia rupture will trigger the northern San Andreas, or whether that pairing mechanism will skip the next event entirely. They do not know how much warning shake alert will be able to deliver to different communities given the specific location of the rupture's starting point. What they do know is the physics of the locked zone. Energy stored in rock does not disappear on its own. It waits. The 300 plus years of plate motion that has accumulated since 1700 represents a physical quantity of stored elastic energy that has only one possible release mechanism: rupture. The fault will break. The only genuine unknowns are the exact scale, the exact location of initiation, and the timing. For the Pacific Northwest, that knowledge creates a choice. The same choice Japan faced before 2011, and the same choice Japan acted on after. The science is not ambiguous about the threat. It is only ambiguous about the schedule. And waiting for certainty about the schedule before preparing is the same as not preparing at all. The ghost trees at Nescoin come and go with the tide. At high water they disappear beneath the surface, and the beach looks like any other stretch of coast. At low tide they emerge again, dark and enduring, rooted in the same mud that swallowed them 3 centuries ago. They are not a dramatic warning. They do not pulse or glow. They simply exist every day in the tidal zone between what people choose to see and what the Earth has already shown them. The fault is still locked. The plates are still pressing. The coast is still bending in ways too slow to feel, but precise enough to measure. The ground remembers, even when we don't.